Hello everyone, this is the final lecture of chapter 10, that's 10.2, and is also the final lecture of this course. So firstly, congratulations to everyone for persevering with the course and for continuing to work hard throughout this semester. Your efforts are both recognised and fully appreciated. Let's take a look at the video breakdown for this particular lecture, where we're going to look at some more radical reactions and also try to make some synthetic connections. There are 4 videos for this lecture. The first video revisits the reduction of alkynes and looks at the radical addition of hydrogen using sodium in liquid ammonia, and this results in the transition to an alkyne. The second video looks at the stability of allylic radicals, discusses allylic bromination, and provides then a summary of all the different ways in which bromination or hydrobromination of an alkene is achieved. The third video looks at a number of summary reaction schemes that you can use to act as a revision scheme as we approach the final exam, and then the last video discusses chain radical addition as a way of polymerizing alkenes. One of the reactions that we studied on this course is the addition of hydrogen to achieve partial reduction of alkynes. We know that 2-butene, for example, undergoes partial reduction to give a transalkene using sodium ammonia. But at the time we were looking at ionic reactions, so discussing a radical mechanism would have been a bit confusing. Now, however, we can discuss that radical mechanism. So, sodium is dissolved in ammonia. Ammonia itself is a gas at room temperature and it boils at a balmy -33 degrees Celsius. So gaseous ammonia is condensed to a liquid using the dry ice acetone cold finger, which is at -78 degrees Celsius. This serves as a solvent for alkaline metals, typically lithium, sodium or potassium. Although these metals are only sparingly soluble in liquid ammonia, about 1 to 5 grams of sodium per litre of ammonia, the result is this beautiful blue colour. So the intense blue colour we see is due to the presence of solvated electrons that are swimming around in this ammonia solution. Now, when the alkyne is added, sodium gives up its electron and one of the pi bonds of the alkyne breaks. This forms a carbanion and at the same time a vinylic radical. This can interconvert from the cis version to the trans version, and this is where the stereochemistry of transition comes from. The electrons are arranged in such a fashion that the trans isomer ends up being more stable because of the reduction of steric hindrance between those electron pairs and that lone electron. The anion is then protonated by ammonia, seeing as this is the only acid present in solution, to give the vinyl radical, which is then reduced by a second equivalent of sodium to give a second anion. This is then converted to the alkene product by protonation with that second equivalent of ammonia. So the net process gives you a transalkene and 2 equivalents of sodium amide.
This concludes part A.
In this video we're going to discuss radical stability, including 2 other species, that's the allylic radical and the vinylic radical. Here we can see the relative stability of all of these radicals in a series, and just before we get into the bond dissociation energies, the allylic position is the carbon that is adjacent to the alkene. So we can see the allylic radical where the dot is. Now, if we think about bond dissociation enthalpy, this is the energy that's required to homolyze the carbon-hydrogen bond, and for the allyl radical, this is the lowest, it's 369 kilojoules per mole, whereas for the vinylic radical, this is far higher. For the tertiary, secondary and primary radicals, these are stabilized by hyperconjugation. And we see that the bond dissociation energies are steadily increasing with the decrease of number of carbon atoms that are surrounding the center that has the unpaired electron. Now, with respect to that vinylic radical, then this is going to have a much higher S character. The carbon that has the radical has increased from being an sp2 center to an sp center, and that half-filled orbital containing the unpaired electron is now held much more closely to the nucleus. And this effect is destabilizing because being closer to the nucleus, the electron affinity of that orbital increases. So you'll need to be aware of vanillic radicals, but you'll certainly need to understand the stability of allylic radicals and their selectivity in reactions. So now we know the destabilizing effect of vanillic radicals, in other words, they don't form very readily. Let's discuss why the allyl radical is the most stable in this series. Do you have any ideas about this? Well, pause the video and resume when you're ready. The answer will be revealed on the next slide in 5 seconds. When the free radical is adjacent to a pi bond, there is a significant stabilization to be obtained if the p orbitals are all in a line. That is, they can overlap, or we may say conjugate with each other through resonance. Overlap is increased and the molecule's overall energy lowered if the shallow pyramid is flattened out. So it is actually a good approximation to think of a free radical adjacent to a pi bond as being sp2 hybridized. So what does this all mean? Well, the electron deficient free radical can be delocalized over multiple carbons. So therefore, radicals are stabilized by resonance just like carbocations or carbanions are. Next, we're going to take a look at how this affects the reactivity in a bromination reaction. In an allylic bromination reaction, we're introducing a new reagent called NBS, and this stands for N-bromosuccinimide, and it acts as a brominating agent. The usual conditions of heat or UV light apply. You may be asking why it's important to use this reagent, and why don't we just use bromine? Well, the answer is that you could use bromine, but it would have to be in trace amounts. Unlike radical substitution, which replaces the allylic hydrogen because of its low bond dissociation energy, the addition of bromine to an alkene results in the bromination of that alkene to form the Vic dihalide. And this would be a competing reaction. As organic chemists, we're in the business of trying to minimize competing reactions so that we get to our desired product without the need of lots of purification steps, because these require both time and energy. There are other advantages to using N-bromosuccinimide over bromine, which we'll now discuss on the next slide. You won't ever have had the pleasure of working with bromine, but this dense orange liquid is not at all pleasant. First of all, bromine liquid produces fumes readily. You've only got to open the bottle and orange fumes start spewing out everywhere. And if you haven't put the bottle deep enough into the fume hood, you'll soon be savouring that unforgettable aroma of bromine mixed with hydrobromic acid in your nostrils. Not a pleasant experience. Secondly, bromine as a liquid is really dense. Its density is about 3.19, and therefore drops of it tend to fall from whatever piece of glassware you're using to try and dispense it. And this leaves a little trail of violently fuming orange puddles behind. Now in contrast, NBS, this N-bromosuccinimide, is this white crystalline solid which is much easier to weigh and is also easier to work with at a practical level. And N-bromosuccinimide does pretty much the same reactions as molecular bromines. So attached to the electron withdrawing nitrogen of succinimide, the bromine has a partial positive charge and is also able to act as an electrophile. So we use NBS largely for allylic bromination. This is the most common use that I'm telling you about now, but it can also serve as a replacement for bromine in the formation of bromohydrins. Any case, let's take a look at how the mechanism of allylic bromination works. Here is an overall reaction scheme whereby propene, this is the simplest allylic system, is converted to allyl bromide via NBS in the presence of UV light. So in the initiation step, the N-bromine bond of NBS cleaves, and this produces a resonance stabilized succinimide radical, as we see here. However, this reaction also produces a bromine radical, which is then taken into the propagation step. NBS is able to abstract a hydrogen to become succinimide, where bromine is replaced by hydrogen. There is typically trace amounts of hydrogen bromide alongside MbS. We'll see this reagent again on the next slide. After initiation comes propagation. The bromine radical abstracts an allylic hydrogen because it has the lowest bond dissociation energy, forming the corresponding allylic radical, and also forms hydrogen bromide. Remember, the allylic radical produced is resonance stabilized. The hydrogen bromide that's produced in this hydrogen abstraction step reacts with MbS, and so this keeps molecular bromine at a low but steady concentration during the course of allylic bromination. You don't need to know the mechanism by which the reaction in the middle occurs to produce molecular bromine. The main purpose of this reaction, I reiterate, is to keep the concentration of molecular bromine in this reaction mixture low. As usual during propagation, the next step in the propagation stage is for the allylic radical to rapidly abstract a bromine atom from molecular bromine. And this produces allyl bromide and a bromine atom, which continues to feed the chain reaction. That stage happens very quickly and is also useful in keeping the concentrations of both hydrobromic acid and molecular bromine at a minimum. Termination of the reaction occurs in the usual way, whereby two radicals meet to end the process. The next question that we'll deal with is what happens if we have the formation of two different allyl radical centers. How does this affect both the regio and stereoselectivity of this reaction? Well, let's take a look. When MbS reacts with butadiene, we now see how resonance comes into play and can be used to explain the distribution of these regio isomers and the minor constitutional isomer. The bromine radical from MbS will abstract the allylic hydrogen just like before, except this time there are two possible resonance structures that will form. One is a secondary allylic radical which is stabilized by hyperconjugation, and the other one is a primary allylic radical which is not as stabilized by hyperconjugation. So this means that bromine abstraction will more likely occur at the position that contains the more stabilized radical species as indicated by the major products. It's also worth reinforcing the idea that the reaction is not at all stereoselective. If we think of the allylic radical as being essentially planar, then bromine abstraction can occur from either above or below the sp2 hybridized center, resulting in these enantiomers. This is a racemic mixture. The other minor product results from the less stabilized primary allylic radical, and there is no chiral center in this product. We've now seen a number of ways in which an alkene reacts with an electrophilic bromine containing species. Let's spend a little time now recapping these on the next slide. Only the major products of these reactions are shown on this particular slide. Bromination is the only reaction here that occurs by a truly ionic reaction to yield the anti-addition products that we see. The stereo bonds on the primary carbon are included to highlight the fact that this is anti-addition, but of course this is really an achiral center. The Markovnikov addition of hydrogen bromide proceeds via an ionic reaction, whereas the anti-Markovnikov addition proceeds via a radical addition where hydrogen peroxide or an organic peroxide is used to achieve the anti-Markovnikov regioselectivity. So the regioselectivity for these reactions are different, but neither reaction is stereoselective. Finally, the radical substitution reaction occurs when MbS is used, as overall the allylic hydrogen is replaced with a bromine atom. This yields the major products, which are shown as a racemic mixture.
This concludes Part B.
In this video, I'd like to highlight the importance of mind mapping to build up your ease in moving between functional group conversions. This will help you build up a retrosynthetic and synthetic toolbox. This slide includes the recently covered radical substitution, whereby alkanes can be functionalized by the introduction of a bromide atom, thus forming an alkyl halide. It's then possible to move from this alkyl halide to a number of functional groups, i.e. an ether, or an alcohol, or an alkene. The bridging functional group is the reaction of alcohols, which can lead to alkenes, protected alcohols, derivatized alcohols, which become better leaving groups, and this is en route to ethers, for example, or the formation of alkenes. And let's not forget, of course, that alcohols, when reacted via oxidation, can produce other carbonyl-containing compounds through oxidations. So that might be an aldehyde, or a carboxylic acid, or a ketone. The reactions of alkenes and alkynes are numerous, so hence I've summarized these on the next couple of slides. Let's take a look at that now. There are numerous reactions that can occur with alkenes. All of the relevant ones I have summarized on this slide as being either addition or oxidative cleavage reactions. I've left blanks here so that you can think of the necessary reagents to get from the alkene to the products that are shown. Pause the video and try to complete this without your notes. The slide advances after 5 seconds to show the completed slide. See how many you got right. How many did you get right? It might be an idea as you begin to revise for the final to make some flashcards. Let's try another one now for the alkynes. Here is a similar exercise for you to complete for the reaction of either terminal or internal alkynes. Again, pause the video and see how many of the reagents you were able to correctly identify for these addition and oxidative cleavage reactions. The video resumes after 5 seconds to reveal the answer slide. Here are those reagents. Did you get them all? Let's take a look at the last slide of the video to review oxidation and reduction reactions. Here are some oxidation ladders for primary and secondary alcohols side by side. Remember that only primary alcohols for this course will undergo partial oxidation and the corresponding carboxylic acids partial reduction. Although I've provided examples of the reductants lithium aluminium hydride and sodium borohydride, only sodium borohydride is chemoselective in that it will not reduce neither carboxylic acids nor esters. Likewise, the best choice of oxidants are PCC for a chemoselective partial oxidation of a primary alcohol to an aldehyde. The use of chromic acid, which is formed in situ, fully oxidizes a primary alcohol or an aldehyde to its corresponding carboxylic acid without the chance of affecting any other alkenes within the same molecule. The second oxidation ladder is specifically for secondary alcohols or ketones, depending on where you're starting from. So, in conclusion, we see that it is possible to use either sodium borohydride or lithal if you're going to perform a reduction of a ketone, or it is possible to use PCC or chromic acid if you're going to oxidize a secondary alcohol. In conclusion to this video, and as part of building your familiarity as you revise, try to now think of a reaction scheme that incorporates carbonyl compounds. Play around with pathways. See how many different reactions you can perform. While you do this, think about competing reactions, regio and stereoselectivities. And I guarantee you that this is a very useful way of revising.
This concludes Part C.
This is the final video of the course, and we're going to be discussing polymerization of alkenes via the chain radical addition mechanism. This leads to large polymeric structures that feature in everyday materials. We're all familiar with plastic carrier bags or even cling film. At a molecular level, this is formed using chain radical addition. The double bond is reduced to a growing alkyl chain, in this case, that came from an alkene monomer. Polyethylene, or polyethylene as it's known, is made of repeating monomeric units that were the alkene ethene, or is also called ethylene. M and N in the polymer and also in the monomer represent very large numbers, typically anywhere in the range of 2,000 up to 20,000 units. Let's take a look at some more of these polymers and see how by changing the hydrogen atoms on just this ethylene molecule that we can affect the physical properties of polymers that we encounter in our everyday material world. Irrespective of chain lengths, one of the things we can observe here is that polymers are easily recognized, and they are done so by placing brackets or parentheses around the carbon framework which was found in the original monomer unit. So in the first instance, we see that polypropylene came from the monomer propene, and that the two pink carbons just represent this chain continuing to repeat. Simply exchanging one hydrogen for a methyl group gives rise to a particularly strong material that you may even be sitting upon while listening to this video. Alternatively, if you exchange one of the hydrogens for a chlorine atom, this leads to a polymer known as polyvinyl chloride, and this is shortened to PVC. It's got some flexibility, so it's often used for tubing or even making clothes. Likewise, the same is true for polyacrylonitrile. One other very important and marketable polymer is called Teflon, and Teflon is polytetrafluoroethene, and this comes from tetrafluoroethene. Now, this is a very hydrophobic substance, so it's not going to get wet by water or any water-containing substances. In addition to that, because the PTFE contains these fluorocarbons, these have high dispersion forces due to the high electronegativity of fluorine, and so there's a very low friction coefficient for this solid. So in other words, it makes for a non-stick coating found in pans and other cookware. There are lots of materials like this. Lastly, we see polymethyl methacrylate, all of which come from this chain radical addition. So while these properties are all very interesting, let's see how some of these polymers are actually made. Sorry, I couldn't resist one last example. Polystyrene is an incredibly diverse material, as you can see from this slide. Let's see how it's made. Virtually all of the monomers described on the previous slide were subject to radical polymerization. Since this can be initiated by traces of oxygen or other minor impurities, pure samples of these compounds are often stabilized by small amounts of radical inhibitors to avoid unwanted reaction. When radical polymerization is desired, it must be started by using a radical initiator such as a peroxide or certain azo compounds. The formulas of some common initiators and equations showing the formation of radical species are seen on this slide. But let's have a look at a peroxy example. In this example, we're going to have a look at the polymerization of styrene to form polystyrene. So the first two equations illustrate the initiation process, and the last two equations are examples of chain propagation. So in the initiation process, what happens is that an organic peroxide is broken apart by heat to form two alkoxy radicals, and it's the alkoxy radical that is added to our polystyrene monomer, and each monomer unit then adds to the growing chain in a manner that generates the most stable radical. Since carbon radicals are stabilized by substituents of many kinds, there is a preference for head-to-tail regioselectivity in most addition polymerizations. Because radicals are tolerant of many functional groups and solvents, including water, radical polymerizations are widely used in the chemical industry. In principle, once started, a radical polymerization might be expected to continue unchecked, producing a few extremely long chain polymers. But in practice, larger numbers of moderately sized chains are formed, indicating that chain terminating reactions must be taking place. Let's take a look at a couple of these on the next slide. The most common termination processes are known as radical combination and disproportionation. These reactions are shown on this slide by these equations. The growing polymer chains are coloured blue and red, and the hydrogen atom transferred in disproportionation is coloured green. Note that in both types of termination, two reactive radical sites are removed by simultaneous conversion to stable products. Since the concentration of radical species in a polymerization reaction is small relative to other reactants, e.g. monomers, solvents and terminated chains, the rate at which these radical-radical termination reaction occurs is very small, and most growing chains achieve a moderate length before termination occurs. Speaking of termination, this slide concludes this video and also the course.